All right, lesson 4.4, congruence and transformation. So this has a lot of review ideas from last couple sections. We're still talking about translation, rotation, reflections. So for this section, we're going to do a few vocab words, congruent figures, congruence, transformation, tessellations, and translation with symmetry. So not a lot in this chapter. Again, it's kind of a little bit of review. Um, we basically get our other name for our rigid motion. So two geometric figures are congruent figures if and only if there is a rigid motion or a composition of rigid motion that maps one of the figures to the other. Congruent figures have the same size and the same shape. So, this is the first time we're going to get that definition for our congruent figures, but congruent figures have the same size and same shape. So again, that's a very important concept. So I give an example of congruent figures and then figures that are not congruent. Again, we know congruent can be the same, so same size, same shape. Um, let's look at the first example. So identify any congruent figures in the coordinate. So on here, there are at least three figures that are congruent. So the first one, we have the square up there, that's or A, B, C, D. So then that one, if we translate it over and down, it lines up with P and Q. So we can say that those two are convergent transformations, same size, same shape. Then the same thing for these triangles. So we have here F, E, G, and L, K, M. Those are really congruent. Then one more set of triangles with the far two corners of each other. We have triangle HIJ, and we can rotate it around. We can say HIJ, and let's convert it to STU. Yeah. Another name for a rigid motion or a combination of rigid motions is a congruence transformation because the pre-image and image are congruent. The terms rigid motion and congruence transformation are interchangeable. We also learned that in 4.1 about isometry. So three things that all mean the same thing: motion, isometry, and congruence transformation. Now, for the next one, we have example 2. Describe a congruence transformation that maps parallelogram A, B, C, D to E, F, G, H. So looking at these, we have to make sure you match them up correctly as well. So the same order that they appear here. So A has to match up with E, B has to match up with F, C has to match up with G, and D has to match up with H. So keeping that in mind, A and E go together. So first I can move this down, and then I could reflect it. So this could be a divide reflection. Take this down and over. Or if we want to reflect it twice, even the mouse work, it's about A over here. Nope, that would be in the wrong corner. But you could reflect it and then slide it. So we could have a reflection in the translation or a translation and reflection. Either of those will be a solution. Yep. Have an original figure. So it says two sides of ABC as right. The corresponding sides fall from left to right. The reflect on the axis is shown in the image. A prime, B prime, C prime, D prime have the same orientation as the original. Now, if I take that and slide it on down to my translation property, what will do? So down. Now, we can check and verify that the corresponding sides and the corresponding angles are congruent. So we can actually find some different pieces. We can show that they are equal and that they are congruent. We can use distance forming to find the ones that are equivalent to diagonal. We can use the protractor to estimate the angle measure. You can see that the corresponding angles appear to be congruent. So now, the last thing is tessellation. A tessellation is a covering of a plane of one or more congruent figures so that there are no gaps or overlaps. Tessellation has transitional symmetry when the tessellation can be mapped onto itself by a translation. Here, determine whether the tessellation has dimensional symmetry. If so, we would like two characteristics. That we have the tessellation onto itself. So because the translation can map the tessellation onto itself, it has traditional translational symmetry, but such translations are shown below. Two such translations that we mentioned before. Using theorems in congruent situations, composition of two reflections result in either a translation or a rotation. And composition of two reflections on parallel lines results in translation. Our first theorem for this section. Reflections in parallel line theorem. If lines K and M are parallel, then a reflection in line K followed by a reflection in line M is the same as a translation. If A prime is the image of A, then line segment A double prime is perpendicular to K, so KM, and the length of A double prime is equal to 2 times B, where B is the distance between K and M. Lots of stuff going on there. Now, in this example, using the reflections in parallel lines theorem, in the diagram, a reflection in line K, so we have reflection in line K, is going to map GH onto G prime H prime. Once at G prime H prime, we'll reflect again in R. Right? Let's try that again. The diagram reflection of K maps GH, this one, blue, to H, no, G prime, H prime. So that's the red one. The reflection in line M maps G prime, H prime to G double prime, H double prime. Also, HB and H double prime D double prime D, that H double prime D is equal to 4. Name any segments congruent to each of those segments. So we don't have a lot of congruency things marked. That's it. So for GH, there's GH, then we have G prime, H double prime, and triple prime, H triple prime. Does DC equal AB? So DC, AC, AC equals A plus C, okay? The one thing that they don't tell us in here is if they're getting careful marks. Like I said, that there's enough information here, but I just that's a, slide had so many things. All right, one more theorem. A composition of two reflections and intersecting lines results in rotation, as described in the theorem. Reflections and intersecting lines theorem. If lines K and M intersect at point P, then a reflection in the line K followed a reflection line M is the same as a rotation about. Angle rotation is 2 times x or x. X is the measure of the acute or right angle formed by. Example 5, using reflection in intersecting lines. In the diagram, the figure is reflected in a line K. The image is then reflected into the line M, describing a single transformation that maps F to F prime. So here, rather the reflections in intersecting lines there, the reflection in line K followed by a reflection in M is the same as the rotation about. The measure of the acute angle formed between lines K and M is 70 degrees. So by the actions of intersecting lines theorem, angle of rotation is 2 times 70, which is 140. The single transformation that maps F to F prime is a 140-degree rotation about point P. You can check that this is correct by tracing and M and point F and rotating that point 140 degrees. That's it. Okay. And tomorrow in class, again, we should be doing an assignment. Make sure you're all caught up. I'll be doing index cards later this week for a check.